Good morning, students. Welcome to the lecture series of Mathematics 3 for all mechanical engineering students. Myself, Dr. Ankit Acharya, and today is our first lecture. So we will discuss about your syllabus, how many chapters in your syllabus, and what are the main important topics. And after that, we will discuss about our first chapter, interpolation. Okay. So firstly, I want to inform you that this is your Mathematics 3, the name of subject. The credit of the subject is 5 and the total number of units in this syllabus is 10. Okay. So in Mathematics 3, the first 5 chapters are for numerical analysis. Okay. Numerical analysis, and the next 3 chapters are for ordinary differential equation, unit number 6, 7, 8. I'm talking about unit number 6, 7, 8. And after that, unit number 9 and 10 are partial differential equation. So first 5 chapters are for numerical methods. So let's simple discussion about your syllabus. So here you can see that in your screen, the name of subject is Mathematics 3. Okay, the credit of this subject is 5. Okay, and as you all know that there are 4 tests, test 1, 2, 3, 4, and each test have 25 marks. So first chapter is interpolation. So in today we will discuss about interpolation. After that, numerical integration. Okay, numerical integration, right? Second chapter is numerical integration. First chapter is interpolation. Chapter number 3 is the solution of system of linear equation. Okay. Then chapter number 4, here you can see that chapter number 4 is the roots of algebraic and transcendental equation, and chapter number 4 is numerical solution of ordinary differential equation. So these 5 chapters are, we can say, from numerical analysis. Okay. The totally different concept, totally new concept for all the students. Okay. So probably in your test 1, these 3 chapters in your test 1 syllabus. Okay. So chapter number 1, 2, 3. In test 2, the next 3 chapters, chapter number 4, 5, and 6. The chapter number 6, you can see that first order ordinary differential equation. Okay. So unit number 6, 7, and 8 are ordinary differential equation. So unit number 4, 5, 6, these 3 chapters are probably in your test 2. Unit number 7 and unit number 8. Okay. This is also ordinary differential equation. For unit number 7 is higher order ordinary differential equation, and unit number 8 is modeling of ordinary differential equation. Right. Unit number 9, here you can see that unit number 9 and unit number 10. These 2 units are partial differential equation. Okay. So in today's lecture, this is our first lecture. So first we start with our first chapter, interpolation. Okay. So first chapter is interpolation. Now, what is meaning of interpolation? Interpolation is the process. Try to understand very carefully. Interpolation is the process of reading between the lines of tables. Okay, it is the process of computing indeterminate values of a function from a given set of tabular values. So that means, suppose you have a table. The entries of x and y. In x, suppose you have 5, 10, 15, 25. Okay, and the value of y, you can take any one, 10, 20, 35, 95, 105. Okay, now here you can see that in x, finite difference, the difference between any two value, that is a fix. 10 minus 5, 5, 15 minus 10, 5, 25 minus 15, so you will get also 5, 25. Let's here we take 20. Okay, so 20, 20 minus 15, that is also 5. So finite difference. Okay, and some of the methods are for finite difference, like Newton's forward interpolation, backward interpolation, Stirling interpolation. These 3 important methods are for finite differences. Okay, now suppose if you want to find the value of y at 12, right, or if you want to find the value of y at 8. Okay, so for that you have to use this all numerical methods, that is called interpolation. Okay, and these 3 methods, like Newton's forward interpolation, backward interpolation, Stirling interpolation, these 3 important methods are only for finite differences. Okay, for only equal interval, you can say equal interval. For unequal interval, there are another 2 methods, that is Lagrange interpolation method and Newton's divided difference interpolation method. Okay, so let's start with concept. First, try to understand the finite differences. As I explain you, finite differences. Okay, let the function y is equal to f of x, right, be tabulated for the equally spaced value y0 that is equal to f of x0, y1 that is equal to f of x0 plus h, y2 that is equal to f of x0 plus 2h up to yn that is equal to f of x0 plus nh. So here you can see that the value of x, that is x0, x0 plus h, x0 plus 2h up to x0 plus nh and so on, and the value of y that is equal to f of x, you can take any value y0, y1, y2 up to yn. Okay, now to determine the value of f of x, now I want to find the value of f of x for some intermediate value of x. Intermediate value of x, that means between any two, means suppose your x0 that is 5 and suppose your x0 plus h that is 10. Okay, x0 plus 2h that is 15. So clearly you can understand that h is equal to 5. H is nothing but the differences. Okay, 10 minus 5, 15 minus 10. Suppose the next value is 25, 20. So 20 minus 15, that is also 5, right? So clearly you can see that h is 5. Okay, and now suppose if you want to find the value of x, if you want to find the value of y at indeterminate value of x, that means suppose I want to find y of 8, or suppose you want to find y of 12. Okay, the value of y of 8, y of 12 is not given in the table, but using this interpolation method we can easily find out approximate value of y of 8, y of 12 and so on. Okay, so this all about in this chapter. So let's start. Okay, try to understand some operators. Okay, first of all you have to understand the operators, right? So first operator, that is delta, right? Forward operator, y0, y1, y2 up to yn denote a set of values of y, where y1 minus y0, y2 minus y1, yn minus yn minus 1 are called the forward difference operator. Okay, forward difference. So this is delta y0, that is y1 minus y0. Please remember all this formula, very important. Delta y0, that is y1 minus y0, delta y1, that is y2 minus y1. Now try to understand, concentrate on this subscript. Suppose you have 0, so here 1 minus 0. Okay, suppose you have 1, so here 2 minus 1. Got it? Suppose you have n minus 1, so here you have n and n minus 1. Clear? Now similarly, second order, that means second forward difference operator, right? Delta is called forward difference operator. The differences of the first forward difference operator are called second forward difference operator. Okay, and similarly you can also define third forward difference and so on, fourth forward difference and so on. Okay, so delta square y0, that is delta of delta y0. Now what is delta y0? That is y1 minus y0. So apply on y1 and y0 both. So you will get delta y1 minus delta y0. Now what is delta y1? We know that delta y1, here you can see that delta y1, the value of delta y1, that is y2 minus y1 and minus delta y0, the value of delta y0, so that is y1 minus y0. Finally you will get y2 minus 2y1 plus y0. Okay, so suppose in MCQ or in objective, suppose they can ask about the value of delta y0, the value of delta square y0, delta square y1, so you can easily find out using this method. Okay, now try to understand this forward difference table, right? Forward difference table. So x0, suppose first entry is x0, then x1. Now don't forget what is our x1. X1 is nothing but x0 plus h. Then x2 is what? X0 plus 2h. Then x3 is what? X0 plus 3h. Then x4. Okay, so this is your first entry, first column, right? What is your second column? The column of y, that is y0, y1. Okay, I just draw this this vertical line, so you can easily understand our table. Okay, so x0, x1, x2, x3, x4, then y0, y1, y2, y3, y4. Okay, now if you want to make a forward difference table, so in between always skip one line between two entries, right? So between x0 and x1 you have to skip one line, between x1 and x2 you have to skip one line. Okay, between any two entries in any column x and y, you have to skip one line. Okay, so you can easily make a forward difference table. So delta y0, what is delta y0? That is y1 minus y0. Okay, y1 minus y0, here you can see that, right? Then what is delta y1? that is y2 minus y1, y2 minus y1. Okay, y2 is below entry, that is y2, above entry is y1. Then delta y2, if you want to find delta y2, that is y3 minus y2. Okay, y3 minus y2, and delta y3, that is y4 minus y3. Similarly, the next table, that is second forward difference table, here you can see that delta square y0. What is delta square y0? That is delta y1 minus delta y0, delta square y1, that is delta y2 minus delta y1, and delta square y2, that is delta y3 minus delta y2. That means this. Okay, delta y3 minus delta y2, then delta y2 minus delta y1, that is delta square y1, and delta square y0, that is delta y1 minus delta y0. Similarly, you can find out all these entries, that is delta cube y0, that is nothing but delta square y0 minus delta square y1 minus delta square y0, and delta cube y1, that is delta square y2 minus delta square y1, and the last entry delta raised to 4 y0, that is delta cube y1 minus delta cube y0. Don't forget, here again the same concept, subscript, in subscript we have 0, so here 1 minus 0. Okay, degree always less than 1, here 4, so here right side you have 3. Similarly here 3, so here right side you can see that 2 2, right? In a subscript you have 0, so here 1 minus 0. Okay, clear? So using this concept you can easily understand. Now next I want to explain backward difference operator. Okay, so backward difference operator are slightly changed. In this backward difference operator, what is our notation? Nabla. Okay, this is backward difference operator. Backward differences. Okay, right? And backward differences, we use this notation. You can say nibla y1, nibla y2, nibla yn. Now what is nibla y1? Nibla y1 is nothing but y1 minus y0. Nibla y2, that is nothing but y2 minus y1. And nibla yn, that is nothing but yn minus yn minus 1. Similarly, you can define second order backward difference operator. Okay, and in general higher order backward difference operator. This is backward difference table. So x0, x1, x2 up to x4. Okay, what is nibla y1? Now here try to understand that here 1. Okay, in subscript you have 1, so right side you have 1 minus 0. In subscript you have 2, so right side you have 2 minus 1. Here in subscript here we have 3, so 3 minus 2. Same concept. Okay, then 4, then 4 minus 3. Here similarly you can define nibla square y2. So that is here degree 2, so right side you have degree 1. Here, and in subscript you have 2, so 2 minus 1. Here 2, so degree 1. Here in subscript you have 3, so 3 minus 2. Got it? And with the similar manner you can easily make this backward difference table. Now okay, and similarly using this method you can easily find out this backward difference table. Okay, so thank you. So next is the central differences. If y0, y1, y2 up to yn, we know the set of values of y, and we know that y1 minus y0, y2 minus y1, yn minus yn minus 1 are called central difference of y. How we denote this delta notation? Delta y1 by 2. So delta y1 by 2, that is equal to y1 minus y0. Now here right side you can see what is your subscript 1 and 0. So 1 plus 0 divided by 2, that is 1 by 2. Okay, so that's why in this subscript you have 1 by 2. Now y2 minus y1, that is delta, the small delta y3 by 2. Okay, so what is subscript 2 and 1? Okay, so what is 2 plus 1 by 2? That is 3 by 2. So that's why in left hand side you have 3 by 2. Similarly, here you can say that yn minus yn minus 1. So how you can find out that n plus n minus 1 by 2. Okay, so this equal to 2n minus 1 by 2, and that's why this is nothing but n 2n by 2. Okay, so that is n minus 1 by 2. Okay, so this small delta is called central difference operator, and similarly higher order central difference operator can be defined, right? And this is central difference table, same entries x0, x1, x2 up to xn. Just the difference is using notation. Okay, here we have to use small delta y1 by 2, small delta y3 by 2, small delta y5 by 2, and small delta y7 by 2. So same notation, same entries, that is y1 minus y0. The difference is only notation. In forward difference table, we use delta, this delta. For forward difference table, we use this delta. For backward difference table, we use nabla, and central difference operator, we use this small delta. Okay, similarly, you can define delta square y1, delta square y2, delta square y3. Here you can see that 3 by 2 in subscript 3 by 2 and 1 by 2. Okay, so as I explained earlier, that 3 by 2 plus 1 by 2 and divided by 2. Okay, 3 by 2 plus 1 by 2. And we know that 3 by 2 plus 1 by 2. So 4 by 2, so that is 2, and 2 by 2, that is 1. So that's why in LHS you have 1. Okay, so easy to understand, easy to find out the value of the subscript. Okay, delta y5 by 2. Here also you can see 5 by 2, 3 by 2. So 5 by 2 plus 3 by 2, that is 8 by 2, 4 by 2. So that is 2. Here 2. Okay, clear? So easy to understand. And now next, there are some relation between operators. So as I told you, that forward difference operator. Okay, sometimes we use this notation also, delta f of x, that is f of x plus h minus f of x. Okay, this is exactly delta y0, that is y1 minus y0. Okay, delta y1, that is y2 minus y1. Okay, as I explained earlier, backward difference operator, that is nabla f of x, nabla f of x, that is equal to f of x minus f of x minus x, right? So use this, remember this definition, very important. Delta f of x, that is f of x plus h minus f of x. For backward difference operator, nabla f of x, that is f of x minus f of x minus x. Central difference operator, this small delta f of x, that is equal to f of x plus h by 2 minus f of x minus h by 2. Clear? So remember this three definition. After that, shifting operator. Okay, shifting operator, we use this notation, capital E of f of x, capital E f of x, that is equal to f of x plus h. So basically, suppose I want to find E of y0, so that is y1. Okay, E of y1, so that is y2. Just your entry is shift to another place, right hand side, right? So in general, E of yn, that is yn plus 1. Here, E inverse in particular, E inverse f of x, inverse operator, inverse shifting operator. Okay, sometimes we use this notation, inverse shifting operator, that is E inverse f of x. So we use this definition, f of x minus h. So similarly, suppose I want to find E inverse of y1, that is y0. Okay, E inverse of y3, that is y2. In general, E inverse of yn, so that is yn minus 1. Clear? Averaging operator, the averaging operator is denoted by with this notation, mu of f of x, that is equal to f of x plus h by 2 plus f of x minus h by 2 divided by 2. Okay, so we use this averaging operator and the differential operator. Okay, differential operator, I hope this is well known operator for you. This capital D f of x, that is equal to d by dx of f of x. Clear? So capital D of f of x, that is equal to d by dx of f of x. Clear? So there are 6 operators: forward difference operator, backward difference operator, central difference operator, shifting operator, averaging operator, and differential operator. And there are some relation between these all operators. Okay, so relation between delta and E. You can see that there are so many important for in previous DTU examination paper. This question asked so many times. Okay, so delta f of x, that is equal to f of x plus h minus f of x. And what is f of x plus h? That is exactly E of f of x minus f of x. So E minus 1, right? E minus 1. Okay, f of x. So you can easily prove that delta, that is equal to E minus 1. This forward difference operator, that is equal to E minus 1. Okay, and also they can ask about that E is equal to 1 plus delta. Now relation between nabla and E. Okay, relation between nabla and E, right? So nabla f of x, that is equal to f of x minus f of x minus h, using the definition of backward difference operator, right? Here you can see that this is the definition, that what is your nabla f of x. Nabla f of x is nothing but f of x minus f of x minus h, and f of x as it is minus f of x minus h. That can be written as f of x minus h. Here you can see that what is your f of x minus h? T inverse f of x. Okay, so that's why we use that notation, that T inverse f of x, that is 1 minus E inverse f of x. So nabla, you can easily prove that nabla is equal to 1 minus E inverse. Okay, now next, relation between delta, small delta, that is central difference operator, and shifting operator E. So we know that delta f of x, that can be written as f of x plus h by 2 minus f of x minus h by 2. Okay, as I explained here, you can see that central difference operator. This is the definition of central difference operator. Delta f of x is what? F of x plus h by 2 minus f of x minus h by 2. Okay, so just we use that definition here. So delta f of x, that is equal to f of x plus h by 2 minus f of x minus h by 2. Now what is f of x plus h by 2? That is e raised to 1 by 2, shifting operator. Use shifting operator. Okay, so e raised to 1 by 2 f of x minus e raised to minus 1 by 2 f of x. F of x will be common, so e raised to 1 by 2 minus e raised to minus 1 by 2. So you can easily prove that delta, small delta, that is nothing but e raised to 1 by 2 minus e raised to minus 1 by 2. Okay, now relation between nu and e. Nu is the averaging operator, e is the shifting operator. Nu of f of x. Use this definition as I explained earlier. This is averaging operator, right? Okay, nu of f of x, f of x plus h by 2 plus f of x minus h by 2 divided by 2, and nu of f of x, that is f of x plus h by 2 plus f of x minus h by 2. What is f of x plus h by 2? That can be written as e raised to 1 by 2 f of x. F of x minus h by 2, that can be written as e raised to minus 1 by 2 f of x. Okay, so easily you can prove that nu is nothing but e raised to 1 by 2 plus e raised to minus 1 by 2 divided by 2. Okay, and this is quite interesting and important, relation between differential operator capital D and E. Okay, so E of f of x, that is equal to f of x plus h. Use Taylor series for this f of x plus h. That can be written as using Taylor series. Okay, don't forget, using Taylor series. So f of x plus h, that can be written as f of x plus h f dash x plus h square by 2 f double dash x. Okay, and so on. Okay, so here we use Taylor series formula. Now f of x as it is plus h. What is f dash x? F dash x is nothing but d by dx of f of x. What is f dash x? F dash x, that is nothing but d by dx of f of x. Okay, and d by dx is what? Capital D of f of x. So instead of f dash x, I can write capital D of f of x. Similarly, f double dash x, I can write d square f of x, and so on. Okay, f of x will be common. So in bracket we have 1 plus hd plus h square by 2 factorial d square, and so on. So exactly, we know that what is the formula for e raised to x? E raised to x is nothing but 1 plus x square by 2 factorial plus x cube by 3 factorial, and so on. Okay, so here you can see that this is exactly the formula of e raised to hd. See, 1 plus hd plus hd whole square divided by 2 factorial, and so on. So you can write e raised to hd. So what you will get, capital E, that is equal to e raised to hd, taking log on both the sides. So hd, okay, taking log on both the sides, so you will get log e, that is equal to hd log small e, and we know that small log e, that is 1. So log e, that is equal to hd. Okay, so hd equal to log e, and what is e? We know that shifting operator e is 1 plus delta, that we already proved earlier. Okay, so you can write log 1 plus delta. Okay, and using that, try to prove this corollary e raised to minus 1 by 2, that is equal to e raised to minus hd by 2. Okay, so in this lecture we discuss about all operators. There are 6 operators: forward difference operator, backward difference, central difference, averaging operator, uh, differential operator, and shifting operator, and relation between operators. Okay, and how you can find out, how you can make a forward difference table, backward difference table. The entries are same, but just difference is only in notation. Okay, so in next lecture we will understand about what is Newton forward difference interpolation formula, difference, backward difference interpolation formula and try to solve some of the important examples. So up to this, thank you.